This is a musical instrument. It is called a guitar. Specifically, it is a Western-style acoustic guitar. All right. This is called the nut. This is called the saddle. The distance between those two is the length of the string. So if you look at your equation, frequency equals N times V over 2L. L would be the length of the string. V would be the velocity of the wave on the string. And N would be the harmonic number. Now, if I don't do anything to the string, we're going to get the first harmonic, and the velocity is going to be, well, we'll talk about that in a minute, and the length is this particular length, okay? So, what happens if I decrease the length class to the frequency of the note? It increases. When I put my fingers down on the particular frets, all it does is change the length of the string. Right? Decreases the length of the string. And these frets are placed such that they will go up by musical intervals. Now, I can also adjust the velocity on the string by adjusting the tension of the string. If I increase the tension, it increases the velocity and increases the frequency. If I decrease the tension, it decreases the velocity and decreases the frequency. Another thing that determines the speed of the wave on the string is the linear mass density of the string itself. So you can see the higher the linear mass density, the lower the velocity and hence the lower the frequency, which is why this note is lower than that note. Oh, I'll have to do it. Okay, so let's see. Okay, so this is the saddle, this is the bridge, this is the sounding board, this is the sounding cavity. So when I play a note, it vibrates the sounding board, the saddle, the bridge, which vibrates the sounding board, which vibrates all the air inside here, which comes out the sound hole, and that's how this is amplified. Now, we have in here two different bouts. We have the large bout and the small bout. The different bouts are different shapes and are going to then have different resonant frequencies, different resonant wavelengths. The larger bout is for larger wavelengths or lower frequencies. Let's see, what else? Oh, sympathetic vibrations. If you recall, when I play a single note, I'm actually going to hear many notes coming from the guitar. So when I play the single note, and then I mute it, you can hear all the other notes coming from the other strings of the guitar. So we have, as I said, you never hear just that single frequency coming from this guitar. You can hear all those other frequencies at the same time. You can also, let's do this. So this is the fundamental frequency, the first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic. 1, 2, 3, 4, 5. Oh, and to relate harmonics to musical overtones, there's a term overtone in music. The first overtone in music is the second harmonic in physics. The second overtone is the third harmonic, so on and so forth. So unfortunately, we have two different terms for the same thing, but that's the way it is, music versus physics. Okay, so to understand what's going on here, if I take and I put my finger down here on the 12th fret, I cut the string in half. What does this do to the frequency class? Doubles it, right? Because I'm taking L divided by 2, that's on the bottom, so it's going to be doubled. Okay. If instead I simply play a harmonic, I go from the first to the second harmonic. Notice how that also doubles the frequency, because I can change from N from 1 to N to equals 2, right? So this note and this note should be the same. Now, I realize that it's hard to see what's going on there, so let me show you the difference. The difference is I'm pushing my finger all the way down to hold the string down at this fret. Now what I'm going to do is I'm simply going to hold my finger over there. I'm not pushing all the way down, and I'm just holding it at that particular point. Notice that if I put my finger all the way down and I let go, it's going to stop. But if instead I simply hold my finger there and play, I'm getting a harmonic. Now what this means is I'm forcing a node at that location. With the first harmonic, there are two nodes at either end and an antinode in the middle. When instead I do this, I've forced a node at that location, right? So now I have node, node, antinode. I'm sorry, node, 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 and two antinodes. Okay. If instead I want to play the third harmonic, I can put my finger here, and this forces a node at that location, which means we have a node, node, node. It also means that there's a node somewhere up here. But it doesn't matter which one I play because it forces a node at the other location. First, second, third, fourth, fifth harmonics. If you are ever going to be purchasing a musical instrument that has frets, a stringed instrument that has frets, you need to make sure that the 12th fret matches the second harmonic. Because the 12th fret is placed by a human. A human has to identify where to put all these frets. And they need to make sure it's an octave above there. But this, the second harmonic, is placed by physics. It cuts the string in half. It has to. You can't do it slightly off. It doesn't work. It only works right in the middle. Another issue with a musical instrument, for a stringed instrument as an example, when I take and I push my finger down on the 12th fret, I'm taking the string and I'm pushing it down like this, and I slightly lengthen the string, right? Because I'm pushing down on it, which is going to make it so that you have to compensate for that by adjusting the location of the fret, which means that that 12th fret will never perfectly match the 12th harmonic. It will always be off. More frustration. Turns out that the third harmonic of the A string and the fourth harmonic of the E string should match. And when they don't, you hear, just so you, Josh, what do you hear? Beats. And you can use those beats to tune the instrument. Right? Except not quite, right? Because recall that the harmonics are not perfect. Right now it's actually 0.1% off. Would you like to? No, not quite. Sorry, more. Sure. This is an electronic tuner. It's now on, yes? Yes, it's now on. Akbar. Okay, good, thank you. I can't see. I've got to turn it around so you can see it. It's now on. It's now on. Okay. When I play this note, the whole guitar is now vibrating at what should be concert pitch. That ends up vibrating the electronic tuner. So it should say Akbar 440 right there, right? And it says A. And there should be a vertical line almost completely straight up, right? Okay? That's because right now it has sensed that it is actually vibrating at about 440 hertz. And it will sense then when I play this note that it's vibrating at some other frequency and tell me what note that is, right? Because right now the whole guitar is vibrating at that frequency, which is going to vibrate the electronic tuner, which can sense what the vibration is. Electronic tuner. Basic concept. Capo. What a capo does is it simply adjusts the key, if you will, of the guitar. So for example, when I play this, which is a C chord, when I play it down here, if I take the capo and I put it up here on the 6th fret, I do the same exact fingering, and what I get is a different chord. 6 half steps up, or 3 full steps up from a C, which is what note?
6 full steps up from the C.
I'm sorry, 6 half steps, or 3 full steps.
F sharp.
F sharp. So this is an F sharp. So instead of playing in C, I'm now going to be playing in F sharp major.